Hello, everyone. We're going to be going over section 7.1 in this lecture, which is on the inverse sine, cosine, and tangent. So we have 9 objectives in this section, so quite a few. But first, we want to define the inverse sine function. Second, find the value of the inverse sine function. Third, define the inverse cosine function. 4, define the value of an inverse cosine function. 5, define the inverse tangent function. 6, find the value of an inverse tangent function. We're seeing a bit of a pattern here. 7, use properties of inverse functions to find exact values of certain composite functions. 8, find the inverse function of a trigonometric function. And 9, solve equations involving inverse trigonometric functions. So let's get started. So before we get on to our first objective, we just want to review some properties of one-to-one functions. So properties of one-to-one functions, which we would call f, and their inverses we call f inverse, or f to the power of -1. These were discussed in Math 126, so we're just going to be reviewing them very quickly, and they're detailed below. So if we take the inverse, or f inverse, of f of x, so if we're taking the inverse of the one-to-one function f of x, this is going to be equal to x for every x in the domain of the one-to-one function f. Then if you take the one-to-one function f of f inverse of x, this is still going to be equal to x, but now for every x in the domain of f inverse. So we see those are the main differences there. The domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. So we'll just repeat that one more time. The domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. So we see they're just flip-flopped in that sense. The graph of a one-to-one function f and the graph of its inverse f inverse are symmetric with respect to the line y is equal to x. So if we draw the line y is equal to x between the two functions, we see that they will be symmetric about that line. And lastly, if a function y is equal to f of x as an inverse function, the implicit equation of the inverse function is x is equal to f of y. If we solve this equation for y, we obtain the explicit equation y is equal to f inverse of x. So if we ever need to solve for the inverse of a certain function, what we can do is we can flip x and y or switch them out and then solve again for y. All right, on to objective 1, we're going to define the inverse sine function. So we can see that y is equal to sine of x is not one-to-one, since every horizontal line, y equals b, where b is between -1 and 1, intersects the graph of y is equal to sine of x infinitely many times. So if we see our image here, we have y is equal to sine of x, and we see that if we draw a line, y is equal to b, for any value between -1 and 1, we see that that line is going to go through the sine function because it's periodic multiple times. So y equals sine of x is not one-to-one. But if we restrict the domain to -π halves, then y is equal to sine of x on the interval from -π half, so x greater than or equal to -π half and less than or equal to π half is one-to-one and has an inverse. So we're looking at this section here. So if we just focus on that section there, that section is going to be one-to-one because our line y equals b will only cross it once. Therefore, if it's one-to-one, then that means it has an inverse. So the function sine, or sine function, can only have an inverse on a specific domain. So we can obtain the implicit form of the inverse function by interchanging the x and y's to get x is equal to sine of y, where now y is between -π/2 and π/2. The explicit form is then going to be called the inverse sine of x, and it's symbolized by y is equal to f inverse of x, which is equal to sine inverse of x. Sine inverse of x we also call arc sine of x. We will most often use sine inverse of x more often than we use arc sine of x, but if you do end up seeing it at any point, that is what it means. Arc sine of x and sine inverse of x are the same thing, they just have different names. So our definition for the inverse sine function, we see y is equal to sine inverse of x if and only if x is equal to sine of y, where x is between -1 and 1, and y is between -pi/2 and pi/2. Then the inverse sine function, y is equal to sine inverse of x, receives a real number on the interval -1 to 1, which is the domain, and outputs an angle or real number in the interval from -pi/2 to pi/2, which is the range. Then the graph of the inverse sine function can be obtained by reflecting the restricted portion of the graph of y is equal to sine of x about the line y is equal to x. So we see our original y equals sine of x is this purple line here, and our blue line is our inverse sine of x. So we see if we draw our line here, y is equal to x, we see that they are reflected. All right, so objective 2, finding the value of an inverse sine function. It is possible to find the exact value of y is equal to sine inverse of x for some numbers, such as the one in the table below. So in our table here, we have different angles. We have -pi/2, -pi/3, -pi/4, -pi/6, 0, and we have pi/6, pi/4, pi/3, and pi/2. So we can find their exact values according to this table. We can find them fairly simply just by reading into the table. Some values won't be so easy. But we can go on to our first example. So example 1, we want to find the exact value of sine inverse of -1/2. So what we do for this problem is we're going to go ahead and we're going to let theta be equal to the inverse sine function. So we're going to let theta equal sine inverse of -1/2, where we're saying that theta, my cat just knocked over the camera. Anyways, so we say that theta is between -pi/2 and pi/2. So if we've let theta equal to sine inverse of -1/2, what we can do now is we can take sine of both sides. So if we take the sine of both sides, we'll get sine of theta is equal to sine of sine inverse -1/2. And what we see here is that theta is still between pi/2 and -pi/2. So what we have here is an identity that we went over in the beginning. We see f of f inverse of x is equal to x for every x in the domain of f inverse. So we have sine of sine inverse of x. So in this case, we'll see this becomes sine of theta is equal to -1/2. Still for theta between -pi/2 and pi/2. So we see we have sine of theta is equal to -1/2. Now we need to find the actual theta value in this case. And if we look up here at our table, we know our answer is -1/2, which means that our angle must be -pi/6. So we can say that the only angle in our interval, which was from -pi/2 to pi/2, whose sine is -1/2, is pi, -pi/6. So this gives us our final answer here, which is that sine inverse of -1/2 is equal to pi/6. sorry, negative pi over 6, drop that negative there. So there we have it. When solving these problems, you want to take whatever thing that you want to find the value of. You want to set this equal to your angle theta, and then you'll go ahead and essentially remove the inverse by taking the original function of each side. So then you end up with something that looks like sine of theta or cosine of theta, whatever trig function of theta is equal to a specific value. This is kind of where you want to end. And then hopefully it's easy enough that you can read the values from a table or even from a calculator if you have access to it at this point. If it is not a straightforward number, there's nothing wrong with using that calculator to find that approximate value. So, all right, let's move on to objective 3 in this case. So now we're going to define the inverse cosine function. So we define our inverse sine function, now we're defining cosine. So just like the sine function, the cosine function is not one-to-one, just as before, except on the interval 0 to pi. So when we had sine, it was only one-to-one on the interval from negative pi halves to pi halves. For cosine, this is going to be from 0 to pi. Then y is equal to cosine of x, where x is between 0 and pi, is 1-to-1, and has an inverse. So this is the only place that we see cosine has the inverse. So the implicit form of the inverse function is x is equal to cosine of y, where y is between 0 and pi. And then the explicit form, which we actually call the inverse cosine of x, is symbolized by y is equal to f inverse of x, which is equal to cosine inverse of x, which we can also see called y is equal to arc cosine. So once again, you almost often see it as cosine inverse of x or cosine inverse of an input instead of something like arc cosine, but it can come up every once in a while, and just know that those two are the same thing. So our definition here, we have our inverse cosine function, y is equal to cosine inverse of x, if and only if x is equal to cosine of x is equal to cosine of y, where -1 is less than or equal to x, which is less than or equal to +1, and 0 is less than or equal to y, which is less than or equal to pi. Then we see that the graph of y is equal to cosine inverse of x can be obtained once again by reflecting the restricted portion of the graph of y is equal to cosine of x about the line y is equal to x. So we see it always be reflected about this line y is equal to x. So if we look at our function here, y equals cosine of x is in this pink purple color. So we see this is what our original function will look like between 0 and pi. And our blue function here, this is our cosine inverse function, which we see is obviously reflected about this line. So, all right, objective 4, we want to find the value of an inverse cosine function. So it's possible to find the exact value of y is equal to inverse cosine of x for some numbers, such as the ones listed in our table below. So we have a table this time as well, so we're going to do the same thing as we did in example 1 here. So example 2, we want to find the exact value of cosine inverse of -√2 over 2. So remember, just like last time, we're going to let our angle equal cosine inverse of -√2 over 2. So we're going to let theta equal cosine inverse of -√2 over 2. Then we want to take cosine of each side. And when we do that, we'll end up with cosine of theta is equal to cosine of cosine inverse -√2 over 2. And remember, this is for theta between 0 and pi in this case. So we have our original function of our inverse function, which from our last problem as well, we know is just going to be equal to our input, which was the negative square root 2 over 2. So this becomes cosine of theta is equal to negative square root 2 over 2 for theta between 0 and pi. So now we can consult our table. So if we look at our values here, given by different values of theta, we want to look for negative square root 2 over 2, which we get right about there. And the angle that corresponds to this value is 3 pi over 4. So the only angle on this interval whose cosine is negative square root 2 over 2 is 3 pi over 4. So for our answer, we get that cosine inverse of negative square root 2 over 2 is equal to 3 pi over 4. So once again, with these easier values, it is fairly straightforward, but if you aren't able to find the values, like if they're not in this table or anything like that, then your next step would be using a calculator. All right, so objective 5, we want to define the inverse tangent function. So now we're defining the inverse tangent function as opposed to sine or cosine. So the tangent function is also not one-to-one unless it's restricted on the interval from negative pi over 2 to pi over 2. So tangent is going to have the same interval as sine. Then y is equal to tangent of x, where y is between negative pi over 2 and pi over 2, not equal to negative pi over 2 or pi over 2. Y is strictly greater than negative pi over 2 and strictly less than pi over 2. So if we restrict our y in this case, then this function is one-to-one and it will have an inverse. So once again, make a note to notice that it does not include negative pi over 2 and pi over 2. This is where we have those vertical asymptotes for tangent. Then the implicit form of the inverse function is x is equal to tangent of y, where y is between negative pi over 2 and pi over 2, not including. And the explicit form is then called the inverse tangent of x and is symbolized by y is equal to f inverse of x, which is equal to tangent inverse of x, which we can also call arctangent of x. So once again, we'll most often see tangent inverse of x instead of seeing these arctangents or arccosines, arcsines. But if you do see it, just know they're the same thing. All right, so our definition here then for our inverse tangent function, we have y is equal to tangent inverse of x if and only if x is equal to tangent of y, where x is then in between negative infinity to infinity. So our x value has infinite range in this case. And our y value, which is acting as our domain, is between negative pi over 2 and pi over 2 not including. So then we see that the graph of y is equal to tangent inverse of x can be obtained by reflecting the restricted portion of the graph of y is equal to tangent of x about the line y is equal to x. So we see our original function here in this pink purple color, y is equal to tangent of x. And then in our blue color here, we see y is equal to tangent inverse of x. So about the line x equals y or y equals x, we see that they are going to be reflected. All right, objective 6. So we want to find the value of an inverse tangent function. So just like our previous examples here, we can find these exact values of y is equal to tangent inverse of x for some numbers as well, such as numbers below in our table here. So the numbers that we're showing in our table, these are easier values to find the inverse trig function of. They are more simple values. They're going to correspond to the values that we're already somewhat familiar with, and that's why we can go ahead and use these tables for them. So for number 3, we want to find the exact value of tangent inverse of the square root of 3. So let's do what we did in our last problems. We're going to let theta be equal to tangent inverse of the square root of 3 for its domain here. So theta is between negative pi over 2 and pi over 2. So we have our domain here. Just like as before, we want to take the original trig function of both sides. So we're going to take tangent of both sides. In order to get our more simplified version. So if we take tangent of both sides, we get tangent of theta is equal to tangent, and let's scoot this down a little bit so we have a little bit more room. Tangent inverse of the square root of 3. Oh, I went a little too fast there. Tangent of tangent inverse of square root of 3. So now we have this function still on the same domain here of negative pi over 2 less than theta, which is less than pi over 2. And using our identity from before, we know that this is going to be equal to tangent of theta is equal to the square root of 3 for negative pi over 2 less than theta less than pi over 2. So all right, on our table here, we're going to look for the square root of 3, which if we go down our table here, we see that square root of 3 is going to be here at the bottom. It corresponds to pi over 3. So this means that the only angle on this interval whose tangent is square root of 3 is pi over 3, which this means that tangent inverse of the square root of 3 is equal to pi over 3. And then we have it for tangent as well. So once again, if you are given a value that is not easily found by one of our key angle measurements or anything like that, it is perfectly acceptable to use a calculator in those cases. So all right, let's go ahead on to objective 7 here.